Hello, thanks for joining us. This is Space Nuts, where we talk astronomy, space science, and all the problems of the world that we cannot solve, and a few other things as well. But coming up on this episode, in fact, we are going to look at some new information that's come from, yes, you're right, the James Webb Space Telescope. It has found 6 new rogue planets, rogue or orphan planets. They're out there floating around. They don't have a star. They've got no mum, no dad. They're just hanging around on street corners, smoking joints. But we're going to find out more about these ones. We're also looking at doubts that have been raised about the existence of dark matter itself. Well, if it's not dark matter, what is it? And if it's dark matter, I don't know. There's been a study done and they've gone, nothing to see here. And we're going to look at some new ideas around the Fermi Paradox and life in the universe. It's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And unravelling the ravelment that is astronomy and space science is Professor Fred Watson. Hello, Fred.
Hello, Andrew. Good to see you.
Good to see you too.
You today.
You're looking rather dapper.
Dapper. Oh,
yes,
God.
Pinstripes suit you.
Yeah. Well, yes, it's the shirt. You see, that's because I spent the morning in far more official meetings than we're in now.
I spent the morning on the golf course.
Well, there you go. Yes, that shows. It does show.
Yeah, well, you can see I'm a bit red in the face, got some sun.
Oh,
yes,
good.
we had a beautiful day today. Spring has just gone,
Right.
Andrew, dropped on us like a giant ball, and it just, all the cold weather just suddenly vanished. Yes, very, very enjoyable. I probably spoke it too soon. Next week we'll have snow.
Except it is coming back. The cold weather's coming back.
Of course it
Yes.
is.
We've had it. We've got 29 degrees here today.
Yeah, we've been up in the
ridiculous for winter.
Yeah, we're expecting. I think we were supposed to get 25 today and 28 on Friday. Yes, it's insane. And yeah, we're still technically in winter. Yeah, I wonder what's caused all that. Let's not go there. But we have got a lot to talk about, Fred. And the first thing is a story that's gained a bit of traction in several websites. And that is a new thing from the James Webb Space Telescope. 6 wandering rogue planets is one headline. Another one says James Webb spots new rogue worlds, orphan planets. I guess we could start off by explaining exactly what a rogue planet is. I think most people have got it in their minds well and truly, but a few might be going, what? What on earth is that? It's it's some. There's all sorts of reasons for them, but they are out there.
That's correct. And I mean, I always think rogue planets it's not a good name for these things.
Makes them sound naughty.
Yes, that's right. It gives them a bad look. Whereas, if you call them orphan planets, then your sympathies are much more with them.
Well, it just sounds sad.
Yeah, sad planets. Yeah. There's an acronym that I remember writing about a long time ago. They were called F-flops. F-flops was free floating low something, but I can't remember. I can't remember what it was. I'd have to look it up, and I haven't got time to do that now. But I thought, yes, F-flops kind of. I think it gave them a sort of tick of failure, a cross of failure, really, didn't it? That they just haven't made it. They're flops, really. They haven't made it. And in a way, that is what this story is about, because whilst we've known about rogue planets or or orphan planets for several decades now, some of the first were discovered actually using the Anglo-Australian telescope, if I remember rightly, here in Australia, in the Orion Nebula. So the Orion Nebula is a place, it's a region of star formation. It's a place which became sort of reasonably well known for its orphan planets. But the question about them is where they came from. And there are basically two possibilities. One is that they formed in the normal way that planets form, from the protoplanetary disk around a young star. And so, orphan planets would have formed along with their siblings in that protoplanetary disk. And then something happened that basically kicked them out, sent them wandering off into stellar space with no sun to orbit around. Maybe we should call them banished planets.
Banished planets. They were caught smoking in the school toilets. That's what it was.
I suppose that's the equivalent of a gravitational interaction with another planetary body, which amounts to the same thing, really. You still get kicked out. So did they form in the way that all planets form, the normal planetary formation, and then get kicked out by some gravitational interaction, or did they form as the bottom rung, if I can put it that way, of the star formation process? So when stars form in clouds of gas and dust, which is where we know they are formed, and they form by these blobs of this gas and dust collapsing under its own gravity, and eventually that collapse produces a high enough temperature because of compression that you will get nuclear reactions taking place. Now, the clouds of gas and dust where we know stars form are multifaceted, and there is a suspicion that perhaps some of them, you get little blobs of gas and dust which collapses as though it was going to form a star or a sun, but it doesn't have enough mass in there. So the compression never reaches the temperatures that you need to click nuclear reactions into being. And so that's what you might call the top-down model, where you start off forming a star, but there's not enough material to form that star, and what you get is something with the mass of a planet, and that is, a perfectly reasonable explanation for why these orphan planets or rogue planets exist, and in a way that gets rid of the orphan bit because they've never had a parent star. They've always been objects that have formed directly from the raw material of stars, that's gas and dust.
Yeah.
So this new observation has shed some light on that. And it comes, as you said, from the James Webb Space Telescope. About half a dozen of these orphan planets, rogue planets, flops, whatever you want to call them, have been found without a star to orbit. And they are in the Perseus molecular cloud. It's a region of molecules, as the name implies, which is basically gas, cold gas and dust. And it's in the constellation of Perseus, the Northern Hemisphere constellation. So the planets which have been found have ranged between 5 and 10 times the mass of Jupiter. And this is a sort of critical measurement because there is thinking that suggests anything less than that, than 5 times the mass of Jupiter, would have to have been formed in a bigger planetary system and then kicked out. So there's a sort of lower limit there on the formation of these. And so what you're saying is that, if you were seeing them less than 5 times the mass of Jupiter, then you could point to them having been formed elsewhere in a solar system and then kicked out. But
they were the runts of the litter.
Yeah, in that sense, that's right. Although 5 times the mass of Jupiter is pretty big.
It is. I wouldn't call it that to its face.
No, you certainly wouldn't want to do that. You could get into all kinds of trouble. But so this observation tends to favour the idea that these things have formed as though they were going to be stars, but haven't got that far.
Yeah.
There is another limit that applies to these objects, because anything that's more than 13 times the mass of Jupiter becomes something else. That is what we call a brown dwarf star, because that is the mass in which what you might call low-level nuclear processes kick in. it's basically deuterium burning. They call it fusion of deuterium. So anything above 13 times the mass of Jupiter will be a brown dwarf star.
Speaking of which, Fred, for those who are watching us, I've got a brown dwarf.
Oh, hang on, I'm going to turn my. Oh, so you do, yes.
Yeah. It's a terracotta warrior from China.
Yes, that's right. There you go.
But it fits in the palm of my hand. Brown dwarf.
Is it less than? It must be more than 13 times the mass of Jupiter then, if it's brown. Because that's the
Don't think so.
But just watch out for that deuterium fusion in its interior.
I hope there's none in there.
At the risk of wondering if you and I are talking at cross purposes here, I'll carry on.
Yes.
So more than 13 times the mass of Jupiter, you've got a brown dwarf. More than 93 times the mass of Jupiter, you've got a star.
Yeah.
Because then you've got enough mass to create hydrogen fusion of hydrogen into helium, the normal nuclear process. So it's an interesting set of observations that we've got that might draw a line under the question as to whether rogue planets, orphan planets, whether they form alone in a top-down process, in other words, collapsing star clouds of raw material of stars, or whether they're kicked out of their solar systems. And it looks as though it is the former rather than the latter. Yeah.
So they're independently created, and then they just float off into the ether. And I guess what will likely happen to them is they'll just keep floating around out there doing not much.
Yes, that's right. Indeed, they will. They will evolve in a slow sort of way. They're almost certainly gas giants. There is just one other sneaky input into this debate that came from these new observations, and that is that one of these rogue planets looks as though it has its own protoplanetary disk. In other words, a miniature version of what the solar system would have looked like in its early history, where the planets were formed, or what a solar system looks like. It looks as though there's a sort of tiny replica of a solar system being formed around one of these rogue planets, which again points to the top-down formation mechanism. In other words, they're formed by the collapse of small clouds of gas in a molecular cloud.
That's fascinating. I also think during this study they found a brown dwarf that had its own planet. So that what would you call that? That's not they're not rogue planets. That's
you might almost call it a binary system, because the brown dwarf is low mass, the planet's probably quite high mass. The difference between one and the other is one's burning deuterium and the other isn't.
Yeah. Wow. There's so much. This James Webb Space Telescope is starting to reveal to us, and even though it's, which I've mentioned before, opening up so many more questions, it's also managing to answer some questions. And we're only in the early phases of its role, its mission. Who knows what else we'll discover? But if you're interested in reading that story about rogue planets, just do a search for it. There are so many platforms. Space.com's done something on it, Cosmos Magazine. Or if you want to put yourself to sleep and read the whole thing, it's in the Astronomical Journal. That's where they publish the official paper.
Indeed, I did.
Yes. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Roger, you're loud and clear here also.
Space Nuts.
Now, Fred, doubts have been raised about the existence of dark matter. We get a lot of questions, surprisingly, about dark matter. People wanting to know what it is, how we've managed to find it. We haven't actually identified it. We just sort of know it's there because it has to be, otherwise things wouldn't add up. But now a new study has been published that's basically said, hey, we've looked for this stuff and can't find it, can't exist.
Yeah, nobody's saying it can't exist.
Oh, I know. I just threw that in there for topical humour.
Well, yes, yeah, yes. Don't misquote anybody though. That
No.
would be a mistake. So, yes, so it's some results from a dark matter particle detector, which is looking specifically for one candidate particle for the dark matter problem. So, quick recap, without there being something called dark matter, galaxies wouldn't hold together. They'd rotate too fast to hold themselves together, and that's one of the main reasons why we think dark matter is present. Plus the fact that we see evidence for it with gravitational lensing and things of that sort. But it's not detectable by normal means because it doesn't seem to interact with normal particles in any way other than by gravity. It doesn't interact, from a nuclear standpoint. It doesn't interact from any kind of electromagnetic interaction. In other words, interaction with photons. None of that. Doesn't want to know. But it seems to exist. Now, multiple candidates have been proposed for what that particle might be. And indeed, some people think there might be a whole zoo of different dark matter particles, like there are with normal matter particles. When you think of the 16 fundamental particles, 17, I think, if you throw in the Higgs boson, in what we call the standard model of particle physics. So one of the proposals has been something called a WIMP. And the WIMP is the weakly interacting massive particle. And a WIMP has particular characteristics, sort of particular expected mass in order to provide the kind of gravitational pull that we think dark matter has. And so this particular experiment was tuned to look for WIMPs, specifically to look for WIMPs. And it's a detector that is called Lux Zeppelin, and I think that's an acronym, but it's usually just contracted to LZ, Lux Zeppelin, or LZ, if you're on this side of the Pacific. A number of scientists have been involved with this, US scientists. It is basically a US facility. It's located I was going to say a mile and a half, but it's actually more like a mile, 1.5 kilometers underground at something called the Sanford Underground Research Facility. And it basically consists of an enormous tank of xenon and a lot of very sensitive light detectors, photomultiplier tubes, as they're called, to detect any collision that might be produced between a WIMP and a normal particle that would produce electromagnetic energy, in other words, light. And so people might be thinking, wait a minute, Fred just said that it doesn't interact with normal particles. And now he's saying that it does. And the bottom line there is that we think it might do, but very, very rarely. In other words, there might be very sparse numbers of interactions between normal particles and the fabled dark matter particles. And what that then leads you to be able to predict, okay, if you've got an interaction between, say, a proton and a WIMP, what will you get? And the theoretical nuclear physicists who think about this stuff can predict what kind of gamma ray spectrum or light spectrum you might get from such an interaction. And that's what these detectors are looking for, those characteristic signatures that you might get from a hypothesized WIMP hitting a real particle, something that we know is not just hypothetical.
Yeah.
Well, they have run this experiment now for, I think, 280 days altogether.
Yep.
And not found anything. And so that means that they can say that these WIMPs don't have a mass bigger than 9 giga-electron volts. So a mass, when you're talking about subatomic particles, is measured in electron volts. 9 giga-electron volts is actually quite high. For example, the particles that you might detect from the Large Hadron Collider are in the basically they're in the tera electron volt level, so they would detect more than this. But this particular experiment is saying nothing bigger than 9 giga electron volts is a whim. They don't exist if their mass is bigger than that. However,
Yeah.
that's
I knew there'd be a but.
Yeah, because a different detector might be able to detect more massive particles, but we haven't got that yet. However, again, one is coming because the university, actually, I think it's a consortium of universities in Australia, are putting together a detector known as SABRE, a nice name, SABRE, and it's down inside another mine, this time in Stoyle in Victoria, well-known town in Victoria, in the southern part of Australia, and that will come on stream next year. The SABRE detector will come on next year. It'll come on stream next year, and it has a different category of detection for dark matter. It's looking for something different rather than just collisions. It's still got a target, not liquid xenon like the Lux Zeppelin has. It's a target that is a mixture of sodium and iodine. So different chemicals that might react to some sort of particle interaction that they think they may be able to detect. I think the Stoyle SABRE detector scientists are a bit more optimistic that they might find something with their new detector when it comes on stream next year.
So the bottom line is they've run this 280-day study and basically said, look, we can't find anything that you could identify as a dark matter particle, and it falls within the search area of these parameters. But we can't look any bigger than that, so we can't find them. They don't exist in this spectrum, but there could be particles that are larger than that we can't find, and we haven't got a machine that can do it yet, but there's one coming.
That's the bottom line. Very beautifully put, Andrew. You ought to be a journalist. And so that's right.
I'm too honest for that.
Yeah, you probably are. The bottom line is the fact is that we know there is something there because astronomy tells us that we're missing something completely. And the best candidate from all the research that's been done is some kind of subatomic particle. And that's why you've just got to do these experiments and hammer down or maybe open up the space within which you're looking. And as you say, it's these various parameters that are being defined by these different instruments. So I hope we'll talk about Stoyle next year when it's switched on. Maybe the first thing it'll discover is a dark matter particle.
Well, we hope so, yes. It would be good to find one, and then we'll ask it a lot of questions because it needs to come up with answers.
Yes.
We've been sitting here wondering for so long now. If you'd like to chase up that story, you can look it up on the ABC News website. That's ABC Australia. But you can also go to the LZ Dark Matter Experiment website, which I found while you were talking, Fred, lz.lbl.gov. So that's got everything you need to know about the study and how it worked and what they did and all these big numbers that are too hard for my brain. But check it out. Sorry?
Excellent.
Yes, it is. It is. This is Space Nuts with Andrew Dunkley and Fred Watson.
0G, and I feel fine.
Space Nuts.
Okay, Fred, just as elusive as dark matter, although the difference being we probably know that dark matter exists, we don't know if extraterrestrial life does. And once again, the Fermi Paradox has been put under the microscope or the telescope or whatever scope you want to use. And questions are being asked, some new ideas about life in the universe or not. What's going on?
Yes, a paper by a person by the name of, I guess it's Vorhin Rakic.
Sounds about right.
I'm probably really mangling that, really. Who is a scientist, Vorhin is a Serbian philosopher. He's somebody who thinks about these things and has published a paper in the Journal of Astrobiology, which I have in front of me at the moment. The International Journal of Astrobiology. The paper is called A Non-Anthropocentric Solution to the Fermi Paradox.
Oh, I like the name of that.
Yeah, and that's right. So it means we're thinking in a too limited a fashion. That's the bottom line. That that extraterrestrial life may have so different set of characteristics to human or to terrestrial life that we're just missing it completely. And that's what he means by non-anthropocentric solution.
I haven't heard the whole story yet, but I reckon he's spot on.
Yeah.
I think that could well be the answer.
It's sort of what what people urge us to do. We get questions from people saying, but have you thought of life that was based on silicon rather than carbon and things like that? And yes, we've done.
Yeah,
methane.
Yeah, we have talked about it.
All of those, we've thought about that. But Professor Rakic is urging us to be even more broad in our thinking. So what he suggests is that the normal explanations, and there's several people have proposed explanations, that they're all too anthropocentric. They're putting humans in the center of the picture, as phys.org has put in their article about this.
Yeah.
And suggests that alien life might be unobservable to the senses that we as humans have developed. This philosopher is clearly a very profoundly thinking person in the field of this kind of approach. He's basically works at the Center for the Study of Bioethics, University of Belgrade, and clearly spent a lot of time thinking about this. I'm trying to think of how we can summarize it. Let me just go back to the abstract for his paper, because he's classifying the solutions to the Fermi paradox in 4 different categories. And this is what his paper discusses. So the categories are, first of all, exceptionality solutions. That means we are exceptional, that there isn't any other life in the universe. Number 2 is annihilation solutions. That is that extraterrestrial intelligence doesn't last very long. It gets annihilated one way or another, either by natural causes, a supernova wiping out life, or
self-infliction.
Self-inflicted ones, exactly, the ones that we naturally think about, wars or even viruses, runaway viruses, things of that sort. And then communication barrier solutions. Sorry, I said there were 4. That's only 3. That means that there's no ability to communicate. And I can imagine one scenario with that might be, for example, if there is extraterrestrial intelligence in the oceans of Enceladus or of Europa, where there's no way of penetrating that ice covering, the glass ceiling, if I can put it that way. You can't get through that. So we would never know about that. So it's a communication barrier. But then he says, really, what we've got to do is take humans out of the equation altogether, forget about human life, and look at the broader context, what sort of life there might be, whether it's life that exists as inorganic matter or, some sort of entity that we are not capable of perceiving. And it's I think what he's doing is setting the groundwork for possible future thinking about this. And in fact, the last line of the abstract of his paper is, in the light of the revolutionary developments in theoretical physics, it is likely that in the future, these developments will be reflected in increasingly non-anthropocentric solutions to the Fermi paradox. In other words, people thinking more outside the box.
You know what? I think that's a great way to. It's a great idea to consider that, because I think he went on to say that some of these entities could exist as made up of dark matter or dark energy, or the things we've been talking about that we can't detect.
Yes,
but
yeah, that's right.
Yeah, that's a possibility. And I love the way he talks about how we perceive the intelligence of other creatures on Earth, like whales and dolphins. But what do they think of us? Do they look at us as intelligent? Maybe they don't. Maybe they just go, look at these dimwits, they can't even swim.
That's right.
And how insect life perceives humans. Do they look at us as intelligent creatures? I think not. They probably they may not even recognize us as alive. And that's where he's coming from.
Yeah, that's right. That's where he's coming from. It is. I think you're clearly enamored by the ideas that he's putting forward, as am I have to say, Andrew.
It's an interesting way of looking at it, and it sort of opens the whole world of science and technology and astronomy to being more philosophical, being using philosophy as a way of analysing possibilities, probabilities, and even things that are so far out of the norm that we haven't even looked there, but maybe we should.
That's right. I feel I've not done this professor a service in terms of my explanation of his theory. But the paper actually, if our listeners can check it up on it's one you can look at online. See, in the International Journal of Astrobiology, it's called A Non-Anthropocentric Solution to the Fermi Paradox. It's very beautifully laid out. I'm not used to reading papers by philosophers, but this is really neat. And the three types of solutions that I mentioned, he lists them here. The exceptionality solutions include the Earth is an exception, or intelligent life is an exception. And that's the one that I've tended to trot out a lot in recent times. The annihilation solutions include periodic annihilations of intelligent life caused by natural events. Advanced forms of intelligence have the tendency to destroy themselves or to destroy others. And then the communication barrier solutions, of which there are many, they broadcast signals that are only detectable for a short space of time. Extraterrestrial intelligent life may be incomprehensible to humans. That's what the one you were talking about in regard to insects and things.
Yeah.
They may reside too far away from humans. It's a really interesting list of reasons why the Fermi paradox might still be a paradox. And then the alternative solution that he presents is itself a really interesting set of reading. I'd urge anybody who's interested in this problem to have a look at the papers.
Yes, indeed. You can read the story on phys.org, phys.org as well. So, or the International Journal of Astrobiology. Yeah, it's a good one. It's a really fascinating story. Gets you thinking outside the box. Love those sorts of theories. That wraps it up, Fred. Thank you so much.
It's a great pleasure, Andrew. It's always good to talk about these things, especially when we get ideas as stimulating as that.
Yes, I'm sure questions will come. Yes. And don't forget, if you want to follow us on social media, we've got the Space Nuts Podcast Group Facebook page, our own specific Facebook page. We're on Instagram and YouTube. And don't forget to hit subscribe if you're a YouTube follower. And thanks, Fred. We'll catch you real soon on the next episode, answering some questions. We'll see you then.
Sounds great, Andrew. I look forward to that.
And thanks to Hugh in the studio, who had all the answers to all the questions we asked today, but we don't let him on the show because we just think he's too clever. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.